This is part 5 of a series on generative adversarial networks. In this video, we will implement unrolled GAN models. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last video, we took a closer look at the learning mechanism of unrolled GAN. In this video, we will look at 3 different configurations for implementing an unrolled GAN, and implement an unrolled GAN and an unrolled DCGAN to see if they improve the mode collapse phenomenon. Before implementing the unrolled GAN model in code, let's first look at the 3 ways to implement the unrolled GAN presented in the paper. Let's look at Appendix B.2 of the paper. A second factor we analyzed is the effect of backpropagating the learning signal through the unrolling in equation 12. We can turn on or off this backpropagation through the unrolling by introducing stop gradient calls into our computation graph between each unrolling step. With the stop gradient in place, the update signal corresponds only to the first term in equation 12. We looked at 3 configurations as follows. The first configuration is the vanilla unrolled GAN without stop gradients seen in the previous video. The second configuration is a simple version of an unrolled GAN with stop gradients. The generator is updated using only the gradients from the final unrolling step. Only the first term of this equation is used. The third configuration is also a simple version of an unrolled GAN with stop gradients, but taking the average over the k unrolling steps instead of taking the final value. If we were to express this as a formula, it would probably look like this. This is done by taking the average of the k gradients of each surrogate loss f. In the second configuration, it would probably look like this. The authors of the paper commented on these configurations as follows. We initially observed no difference between unrolling with and without the second gradient, as both required 3 unrolling steps to become stable. When the discriminator is unrolled to convergence, the second gradient term becomes 0. Due to the simplicity of the problem, we suspect that the discriminator nearly converged for every generator step, and the second gradient term was thus irrelevant. In this video, we will implement the third configuration of the unrolled GANs. Now let's implement an unrolled GAN model in code. Generate a dataset consisting of 8 Gaussian distributions, arranged in a circle like this. This is real data, the same one we used to implement the standard GAN in the second video of this series. Write a function that builds a discriminator model. And we write a function that builds a generator model. Create a discriminator model. Create a surrogate discriminator model to be used in the unrolling steps. And create a generator model. Next, we write a custom class to create the unrolled GAN model, just like we did when creating the standard GAN model before. This class takes as input a discriminator, a surrogate discriminator, and a generator. And it also takes k, the number of unrolling steps, as input. We will use the atom optimizer to train the models D, S, and G. We write a function that copies the parameters of the discriminator to the parameters of the surrogate discriminator. Next, we write a function to compute the loss of the discriminator or surrogate discriminator. The input DS is a discriminator, or a surrogate discriminator model. And the input X and Z are the real data and random noise. We use this formula to compute the loss of the discriminator. Next, we write a function to compute the loss of the generator. We use this formula to compute the loss of the generator. We define a list of metric objects for the discriminator loss and the generator loss. This figure shows the training process of the unrolled GAN we looked at in the previous video. Here, psi is the parameter of the discriminator, phi is the parameter of the generator, and theta is the parameter of the surrogate discriminator. For more information about this, please watch the previous video. Also, this is the third configuration we looked at on the previous page. The update rule of the generator is as follows. We define the train step method. First, we update the discriminator one time. This is when H is set to 1. Sample random noise Z from a uniform distribution. Update the parameter psi of the discriminator to minimize loss D. When computing the loss D, the discriminator model is passed. After the discriminator update is complete, we copy the parameters psi of this discriminator to the parameters theta of the surrogate discriminator. Then the surrogate discriminator becomes identical to the real discriminator. Now we update the generator by updating the surrogate discriminator during unrolling. The surrogate discriminator is used to compute the surrogate loss function f. Repeat the unrolling step k times. Update the surrogate discriminator theta. Update the parameter theta of the surrogate discriminator to minimize loss D. When computing the loss D, the surrogate discriminator model is passed. The list of these variables is theta. Next, we compute the partial derivative of f with respect to generator phi. This is the surrogate loss function f, and since the first term is independent of phi, we only need to use the second term. The second term is loss g. Therefore, we compute the gradient of loss g with respect to phi. We store the gradients in a list to compute the average later. Once the unrolling is complete, we compute the average of the gradients stored in the list. We then update the generator using the average gradients. Later, by repeating the train step method using the fit function, both the discriminator and generator are trained. Now we create and compile the unrolled GAN model. The number of unrolling steps is set to 5. We write a function that observes the distribution of real data X and fake data G of Z. Finally, let's fit this model to real data and observe the distribution of fake data. After 50 epochs, the distribution of fake data is as follows. The red dots are fake data G of Z, and the blue dots are real data X. After 100 epochs, the distribution of fake data is as follows. The fake data is now a little closer to the real data. After 450 epochs, the fake data became similar to the real data. In the standard GAN implemented in the second video, mode collapse and mode hopping phenomena occurred like this. However, we can see that these phenomena disappear in our unrolled GAN model. Let's run this code. Fake data is getting closer and closer to real data. We can see that no mode collapse or mode hopping occurs. Next, let's implement an unrolled DCGAN. Load MNIST dataset. Training an unrolled DCGAN takes a long time, so we will only use 5,000 images. Create discriminator and generator models. These are the same ones we generated when implementing the DCGAN in the third video. We also create a surrogate discriminator to compute the surrogate loss function f. Next, we write a custom class to create the unrolled DCGAN model. This is identical to the unrolled GAN class in the previous code. We create and compile the unrolled DCGAN model. Fit this model to the real data, and we observe the loss history during training. Finally, we use the train generator to generate MNIST images. Let's check the results. The changes in loss D and loss G during training are as follows. The loss history of the discriminator is like this, and the loss history of the generator is like this. The images generated by the generator are as follows. Images of various digits were generated. Below are MNIST images generated by a standard DCGAN and an unrolled DCGAN, respectively, when the number of epochs is 1500. Images generated by a standard DCGAN show a lot of digits 1, while images generated by an unrolled DCGAN show a variety of digits. We can see that the mode collapse phenomenon is reduced in our unrolled DCGAN. So far, we have looked at unrolled GANs. In the next video, we'll look at least squares GANs.